So we derived these two expressions for the Bernoulli equation. So this was for steady flow, and this was for steady and incompressible flow. So let's go through our limitations. So first of all, we'll have a steady flow, otherwise this velocity will not be constant. Then we'll have a frictionless flow. We assume there is no loss of energy due to friction. Okay, then there's no shaft work, so there's no mechanical energy coming in or out of our system. Then we have incompressible flow for this case. There's no heat transfer coming in or out of the system. And we study the flow along a streamline. So let's look at a few cases under which the Bernoulli equation will not work. If we have a sudden expansion, or if we have a long narrow tube, which then that would imply friction. If we have a fan means there's a shaft. If we have a heating section, we add heat transfer. Now, let's assume this foil and the flow around it. So here we'll have a boundary layer, and back there the wake of this foil. But on any other streamline, we can apply Bernoulli between those points. Okay, provided that we stay away from the boundary layer and the wake. Okay. For the case of the incompressible flow, this term we refer to it as flow energy. This has kinetic energy. And this has potential energy. We can rewrite this equation as P divided by rho G plus V squared divided by 2G plus Z is H, which is constant. So this H we can call total head. This term we can call pressure head. This term velocity head, and this term elevation head. Now, for the case of a steady incompressible flow, let's see a few examples. So, let's assume that we have a water tank and an opening here. This water tank is filled with water, and we have point 1 there and point 2 over there, and our fluid comes out at the velocity v2. Okay, so we can assume a streamline between point 1 and point 2 over there here, and we will apply the Bernoulli equation. So we'll have P2 over rho plus V2 squared over 2 plus GZ2 will equal P1 over rho plus V1 square over 2 plus GZ1. Okay, let's see which terms we can ignore. So point 2, we can take it as our reference line. So this term will go away. Also, pressure 1 and pressure 2, we can assume them to be atmospheric, since both sides are open to the atmosphere. So this term and this term goes away. Now, point 1 is moving down. Okay, so there's some velocity, but because the tank is very wide, okay, we can assume that this velocity is very small. So we can say that V1 is approximately 0. So this term goes away too. So now we can relate V2 to the height of point 1, Z1. So the Bernoulli equation can be written as Z1 equals V2 square divided by 2G. Now let's look at another example. We have a pipe, and the pipe broke here, and there is water in here, and from that breaking point there is a water jet merging. Okay. Let's apply Bernoulli between point here 1 and the top of the jet point 2. Okay, so again we have P1 over rho plus V1 square over 2 plus GZ1 will equal P2 over rho plus V2 square over 2 plus GZ2. So again, as we did before, we can assume point 1 the reference height, so GZ1 can be ignored. Now at point 1, because the fluid hasn't started moving that direction, we can say that velocity point 1 will be almost 0, and thus this term can be ignored, but we cannot ignore the pressure that's within the pipe, P1. Okay. This is absolute pressure. Okay. And the same with P2. P2 is exposed to the atmosphere, so P2 is going to be the atmospheric pressure. Now, at point 2, the velocity of the fluid is 0, so this term can be ignored too. So now our equation will turn into P1 minus P atmosphere over rho equals GZ2. This term, we've already talked about it, it's the gauge pressure at point 1. So it's called P1 gauge. Now let's look at one more example. We have a container, maybe a fuel tank for a car, and we siphon a fluid out of it and bring it in the container over here. Okay, so there's a velocity here. We will call this point 2, and this here we call it point 1. Okay, so we can apply the Bernoulli equation between point 1 and point 2. So we'll have V1 over rho plus V1 square over 2 plus GZ1 will equal V2 over rho plus V2 square over 2 plus GZ2. So let's see which terms we can ignore. So first of all, the height at point 2, we can assume it's 0. So this term can be eliminated. Now, point 1 and point 2 are exposed to the atmosphere, and they both have the same pressure. So P1 and P2 can go away. Z1 obviously cannot be ignored. It's the height of point 1. Okay. What can be ignored is, because this container is very big and the flow here just about moves, okay, we can assume that V1 is almost 0. So this term can be ignored. So now we're left that Z1 is V2 squared divided by 2G.